This is a talk given by Rudolf Carnap at the meeting of the American Philosophical Association Pacific Division at Santa Barbara on December 29, 1959, on theoretical concepts in science. For many years it has been found useful in the analysis of the language of science to divide the terms of this language into three main kinds: logical terms, including those of pure mathematics; observational terms, which I shall call for brevity O terms; and finally theoretical terms, or T terms, sometimes also called constructs. It is true that it is hardly possible to draw a clear-cut boundary line between O terms and T terms. That is to say, the choice of an exact line is somewhat arbitrary. But it does not matter exactly where the boundary line is drawn, but roughly speaking, it seems from a practical point of view important to make the distinction between terms like blue, red, hard, soft, hot, and cold on the one hand, not as terms for sense data, but as properties of observable things, and likewise terms for relations among things, one being near the other or greater than the other, and so on. And on the other hand, terms like electromagnetic field and electric charge or charge density and photons and neutrons and so on, terms which occur in theoretical science and for which we cannot claim that we have knowledge concerning singular facts directly by just looking at a thing. So the first, we say, are observational terms or O terms; the second, theoretical terms or T terms. Sometimes they have been called constructs or theoretical constructs or abstract constructs. And then with respect to the sentences, we make a threefold division, as you see it here in where is the diagram? Oh, here. Would it not be better here so that you have place for the second blackboard there?
Well, I can move to the blackboard later.
All right. So here we have the threefold division of sentences on the basis of this twofold division of the terms into sentences whose only descriptive constants are observational, and that is the observation language on the left-hand side, or observational sentences, O sentences. There I make a distinction between the Ls of O, the observation language in the narrow sense, which is logically restricted to a first-order logic, and the extended observation language, which I call LO prime, which contains just the same descriptive terms as LO, but in addition, not only first-order logic, but a rich logic containing the whole of mathematics. It doesn't matter either in set theoretic form or in type theory form. There we have the whole of higher logic, including mathematics. Then on the right-hand side, we have those sentences which contain as descriptive terms only theoretical terms, and in the middle we have then mixed sentences. And the postulates which make out the theory, which constitute the theory, are partly theoretical sentences, and we call them T postulates, as for instance laws of theoretical physics, and partly mixed sentences or correspondence postulates, and preferred C postulates, which are mixed sentences because they contain both theoretical terms and observation terms. They correspond to what Campbell would have called the dictionary between the two languages, what Reichenbach would have called correlative definitions of terms occurring in axiom systems of theoretical physics or any theoretical science, and what Bridgman might have called operational postulates or operational rules. So this is the distinction which we make between terms and between sentences, and one of the most important characteristics of the T terms, and therefore also of all sentences containing T terms, at least if they are occurring not in a vacuous way, is that their interpretation is not a complete one, because we cannot specify in an explicit way by just using theoretical observational terms what we mean by the electromagnetic field. We can say if there is a distribution of the electromagnetic field in such and such a way, then you will see a light blue, and if so and so, then you will see or feel or hear this and that. But we cannot give a sufficient and necessary condition entirely in the observation language for there being an electromagnetic field having such and such a distribution. Because in addition to observational consequences, the content is too rich. It contains more than we can exhaust by the observational consequence. So this is the original setup, and on the basis of that, we want to make a distinction between logical truth and factual truth. I believe that such a distinction is very important for the methodology of science. I believe that in order to understand the essential distinction between pure mathematics on the one side and physics, which contains mathematics but in an applied form on the other side, can only be understood if we have a clear explication of the distinction that in traditional philosophy is known under the terms of analytic and synthetic, or necessary truth and contingent truth, or however you may express it. Now Quine has pointed out that logical truth, really, that here a new distinction should be made. Logical truth in the narrower sense comprises those sentences whose truth is established in deductive logic, plus substitution instances of them which may contain descriptive terms, while there are other sentences which we may regard also as analytic. This example, for instance, as you remember, is no bachelor is married. That is certainly true, but its truth is not a matter of the contingent facts of the world. It is a matter merely of the meaning of the terms. It is true on the basis, in virtue of the meanings of the terms, but in distinction to the logical truth in the narrow sense here, also in virtue of the meanings of the descriptive terms. If we know the meaning of bachelor and the meaning of married, or at least we know or are told by somebody who understands this language that these two terms are incompatible, then we know that the term no bachelor is married, the sentence is true in virtue of meanings alone, so it is analytic, as Quine would propose to distinguish. So logical truth in a narrow sense or logical truth in a wider sense or analytic. And for this letter, for the first, I will take the term L true, capital L hyphen true, as the term for the explicatum. For the second, A true. And my main purpose here is to indicate how we can make the distinction between A true and other true, namely factual true, sentences, not only in the observation language but also in the theoretical language. In the observation language, we know a way of doing it. I explained that years ago in a paper called Meaning Postulates. I would now call them A postulates, and then say every term that is a logical consequence of the A postulate is then A true. This can easily be done in a language like the observation language, where we presuppose that we are in the possession of a complete interpretation of the terms. That need not be done in an explicit way by semantical rules, but just you ask somebody, is this part of the English language completely understood by you? Do you know what you mean by the verbs that you use there? While, as I said before, the terms of the observation language, of the theoretical language, are not completely interpreted. The interpretation which they have is not learned in the same way as the interpretation of terms like red and blue, which we learn, let's say, as we learn our mother tongue, by hearing how they are applied and imitating these applications and making an unconscious general inductive inference. And so we know now what we mean by red, by hot, and so on. But with electromagnetic field it is different. There we cannot simply point and say, by electromagnetic field I mean this and that, or an electromagnetic field having an intensity of so and so much, or vector so and so. We cannot simply point and thereby learn it. We learn it by the postulates. These terms are introduced by the postulates, namely the T postulates, general laws of physics, which connect these terms among each other, which obviously is not sufficient to give any meaning to them. And then the second kind of postulates, the C postulates, which connect these terms with those of the observation language. For instance, the term temperature is connected by the C postulate with observational terms, namely a C postulate which describes how you proceed in constructing a thermometer and constructing its scale, then putting the thermometer in a certain liquid, and then reading a certain number. Then you are told, take that number as the value of the temperature of that liquid. So here we are given rules which connect certain observables with a theoretical term like temperature. And thereby then this term obtains a partial interpretation. Partial because not in all occurrences of the term temperature can we use this operational definition. It works only for let's say, an ordinary thermometer, only in some rather limited interval of the scale. For too low temperatures, for too high temperatures, we must use entirely different methods. So each C postulate applies only to certain cases, and all of them together would not help us to determine temperatures or electric fields and so on, unless we had also the T postulates. So it is then the T postulates together with the C postulates which give interpretation, all of that interpretation that the T terms have, which is not a full interpretation. That we have to keep in mind. But what interpretations they have, they get by the postulates and by the postulates of these two kinds together. Now, when the question is raised how to distinguish between sentences whose truth is due to meaning and other sentences, then, as Hempel has especially clearly pointed out, there is a great difficulty in the theoretical language. Hempel was, with some hesitation, I believe, willing to accept the distinction with respect to the observation language. On the one hand, he is influenced by my way of thinking. We are old friends from the days in Germany. On the other hand, he is also influenced by Quine's skepticism with respect to making a clear distinction between factual and logical truth or meaning truth. And he pointed out that he can hardly imagine how a distinction could be made also with respect to the theoretical language. Any sentences containing either theoretical terms alone or theoretical and observation terms, for the following reason. The interpretation of the T terms is given by these postulates, not by explicit definitions on the basis of the observation language. But these postulates have a dual role. They have two different functions, each of them, or their totality, fulfills simultaneously, namely, they give some meaning to the terms, and they give some factual information to us. That they give factual information is seen from the fact that if the physicist gives his whole theory to us, then we are in a much better position to predict the weather of tomorrow than if we rely only on a few generalizations which can be formulated in the observation language. If you see clouds of such a shape, then tomorrow it will probably rain or something of that kind. So the theoretical system of physics certainly gives factual information. But it gives factual information and specification of meaning simultaneously. And Hempel said that makes the concept of a truth entirely elusive, because there's hardly to be imagined that we could split up these two functions of the T and C postulates so that we could say this part of them contributes to meaning, and therefore the sentences which rely on that part, they are then, if they are true due to meaning only, the other are factual sentences. So this is the big problem for which I want to propose a solution, namely how to define a truth in the sense of analyticity or truth based on meaning, also for the theoretical language. Now, in order to do that, I first will speak of a device that has already been introduced a long time ago by Ramsey. It is the so-called Ramsey sentence, as we call it today, corresponding to any given theory in the theoretical language, or with mixed sentences. Given in the theory, I write it for short TC, or in a slightly more explicit form, if the observational terms occurring in it, of course they occur only in the C postulate, but let T be the conjunction of the T postulate, C of the C postulate, and TC of both together, then in order to indicate the descriptive terms occurring, let's write it in the following form, as you see it there, TC, and then the observational terms O1 and so on, OM, then the theoretical terms T1 and so on, Tm. And we form from this the Ramsey sentence in the following way. We keep the observation terms unchanged, but we replace the theoretical terms by variables. Let's say for T1, we put for the constant T1, we put the variable U1, for T2, U2, and so on. If it is in a type system, then it must be variables of the corresponding types. And then we prefix the whole by existential quantifiers, one for each of these n variables corresponding to the n theoretical terms. So we presuppose that there is a finite number of theoretical terms in that language. Now, Ramsey showed that this sentence is what I would propose to call for short O-equivalent, or observationally equivalent, to the original theory, namely the total theory of the T and C postulates, in the following sense. We'll say that a sentence S is O-equivalent to a sentence S prime if all the observational sentences, that is the sentences in LO prime, which follow from S, follow also from S prime. So as far as observational consequences are concerned, S and S prime are equivalent. That is meant by O equivalent. Now Ramsey showed that this existential sentence, which we call now the Ramsey sentence, is O equivalent to the theory TC. And practically he drew the following consequence, or he made the following practical proposal. He said the theoretical terms are rather bothersome because we cannot specify explicitly and completely what we mean by them. If we find a way of getting rid of them and still doing everything what we want to do in physics with the original theory which contains these terms, that would be fine, and he proposes to use this existential sentence. You see, in the existential sentence, the T terms do no longer occur. They are replaced by variables. These variables are bound by existential quantifiers. Therefore, that sentence is in the language LO prime, in the extended observation language. And he said, let's just forget about the old formulation TC, about the T terms. Let's just take this existential sentence, and from it we get all the observational consequences which we want to have. Namely, all those which we can derive from the original theory. Now, the form of the system which I propose makes essential use of the Ramsey sentence, but I do not want to take this radical step, at least here in this form which I shall describe now. I rather say, let's keep the theoretical term, let's keep the old form, and but then I introduce certain distinctions in order to make the desired distinction between A truth and factual truth. And I make that in the following way. I wish to split up the theory TC, the theory in its ordinary form, with the T postulates and the corresponding postulate C, in another way, not into T and C, but in another way, into two sentences where the one represents the factual content, and I call that P, that is then the physical postulate, and that is synthetic, and on the other hand, in a part which is only an A postulate, which gives only meaning specification, partial meaning specification, no more is possible here, and does not convey factual information, and I call that A sub T. By A sub O, I mean the conjunction of all the A postulates or meaning postulates which we have in the observation language. I will not give them, so something like no bachelor is married or so might occur there, or warmer is a transitive relation or something of that kind. And then for the T terms, I will give a postulate which I call A sub T. After having specified these two, then I will define A truth in the following way. A sentence is A true if it is a logical consequence of A sub O and A sub T together. I use there the assertion symbol of the Principia for L truth. So that is expressed by what is written there with this symbol. If A, O, and A, T together, L imply S, then I will that, and only in that case will I say that S is an A true sentence. So now I must specify what I mean by P and by AT, and then show that the two together really are no more and no less than the old theory, so that I can regard them as a splitting of the old theory in two parts. And second, that the one really is merely factual, the other merely specification of meaning. And I do it in this way, that I take as the P postulate the Ramsey sentence of the theory, which I write as TC with an upper left-hand superscript R. So RTC, the Ramsey sentence, that I take as my P postulate, as the physical postulate, as the factual content. And then as the A postulate, A sub T, I take a conditional sentence, namely, if RTC, then TC, where the if then is the material implication. So these are the two postulates which I propose, and but this is merely a reformulation of the old theory. This logic equivalent to the old theory. So I want to stress especially this point. I do not propose a new theory. If a theory is given, I merely split it into another way into three kinds of postulates, and I call that correspondingly forms. I call the first form 1, that is the customary form, namely AO, the meaning postulates of the observation language, T and C, and now form 2, AO, unchanged, AT and P, but AT takes something from C and something from T, so AT and P are not simply parts of T and C as they occur in the ordinary formulation, but are entirely reformulated, as you see, for instance, that P is the Ramsey sentence. So the whole of T and C occurs there, but in a changed form, with the theoretical terms having been eliminated and replaced by variables. Now, does this splitting up really, does this system of P and AT really fulfill the purpose which I said it should fulfill? I will not show it, but it can be shown in a very simple way that the following three results hold. I call them ABC, they are written there somewhere. The first is that TC is logically equivalent to P and A sub T. Well, that in the one direction it follows directly from modus ponens, and in the other direction, obviously from TC we can derive any conditional that has TC as a consequence. So this is quite clear. In other words, P and AT together is just a reformulation in another form of the old theory. Second, P is O equivalent to TC. Therefore, and P is in the, as I said before, is in the extended observation language. It does not contain the theoretical terms, but it contains all what we might call the observational content. Therefore, it seems to me that P really fulfills its role. It gives us the factual information as far as observations are concerned, and it does certainly not give us any specification of the meanings of the T terms because they do not occur at all in P. On the other hand, AT is of such a kind that, as result C says, the Ramsey sentence of AT, so imagine AT, RTC implies TC, this whole now Ramseyized, namely in the second part we have some T terms occurring. Replace them by variables V1, V2, and so on, and then put existential quantifiers not before that part, but before the whole sentence. That is then the Ramsey sentence, not of TC, but the Ramsey sentence of A sub T. And it turns out that that sentence is logically true. Since it is a Ramsey sentence, it is in the observation language, and is logically true in the observation language, so it does not have any factual content. In other words, AT does not say anything about the world of facts. So all that it does is it gives us some connection between the terms, namely the T terms among themselves and the T terms with the C terms, of such a kind that it helps to give a partial interpretation for it, and that is the purpose of an A postulate. So in this way I propose to write the theory in the second form. I do not say that this form is essentially superior, so I do not say let's forget the old form, only use this one. The old form is very convenient and for many purposes perhaps more convenient because it is the customary form. We find there the Maxwell laws and the law of gravitation and such physical laws in their customary form, and then we have the C postulates in their customary form, so that is certainly a very convenient form. The second form has only this purpose. If we want to make the distinction between a truth and factual truth, then this form shows this interpretation in a clear way. Once this interpretation has been made, then we might also introduce the term of p-truth, namely all those sentences of the total language L, which are logical consequences of A sub O and A sub T, that is all the A postulates of all the parts of language, and P, the physical postulates, are called p-truth, physically true or practically true. So here we have then in the diagram there of the classification of the sentences of the total language. They fall, of course, into true and false sentences. Among the true sentences, we have a small subclass, the L-true, somewhat larger, including the L-true, the A-true, this is the analytic class, then the P-true, on the other hand, correspondingly L-false, A-false, and P-false, and intermediate then into the indeterminate sense, L-indeterminate, A-indeterminate, which means then synthetic, and P-indeterminate, which means, so to speak, contingent, not determined either affirmatively or negatively by the basic physical laws. So this is the classification of the sentences which we have. And on the basis of this here, I will perhaps first make a reference to publications. The Ramsey sentence has been published posthumously in the book Foundation of Mathematics, which you know, which was published in 1928. It was written some years before that. It has found very little attention until the very last years. Braithwaite refers to it and discusses Ramsey's method in his book, but otherwise very little is to be found in the literature. But then Hempel, in a paper, The Theoretician's Dilemma, which was published in the second volume of the Minnesota Studies for the Philosophy of Science, emphasized the great importance of the Ramsey sentence and discussed a number of methodological questions and logical questions of the language of science on the basis of the Ramsey sentence. And on the other hand, he used it also in order to raise unsolved problems, and among them the problem which I mentioned, which he thought might perhaps not be solvable, namely making a distinction between analytic and synthetic. Now, in addition, he has a more detailed discussion of the whole in an unpublished paper, which will appear in the Schild volume on my philosophy, which we hope will appear towards the end of 1960. It is not quite determined. And what I just explained, my explication of A-true, also including the theoretical language, is contained in my unpublished reply to this paper by Hempel, which will occur in the Schild volume. And a much briefer discussion of it is it has been published in a German language paper, which David Kaplan mentioned, Beobachtung und theoretische Sprache, which has been published first in the periodical Dialectica, published in Zurich 1 year ago, and then the whole double issue of Dialectica is separately published as a Festschrift for Paul Bernays under the title Logica, and there my paper and paper of many other authors has appeared. Now, I want to raise some questions from a philosophical point of view, which I think are interesting from a philosophical point of view. It is the old question that was already raised by Ramsay, namely, could we in some way perhaps get rid of the bothersome theoretical terms and restrict ourselves to the observation language? He did not yet make the distinction between LO prime and LO, but I think he might have envisaged, when he said observation language, the whole, which I now call LO prime. So from now on, when I say observation language, I mean it in the wider sense, including as descriptive terms only the simple observation terms, but a very rich logic. And I shall especially use a special logical symbol, which I shall explain soon, which comes from Hillman. Now, can we restrict ourselves to the observation language and still to do everything that physicists want to do? This is the practical question. Now, Ramsay's proposal is, of course, one way of doing it, namely using the Ramsay sentence instead of TC. But that has certain, not essential objections, only strong inconveniences. Because think of the following fact. If somebody asks a physicist, give me the whole of your theory, then really Ramsay is right that it doesn't make for much greater inconvenience whether he gives it in the old form, a long series of sentences. He says these are my theoretical postulates, and a still longer series of correspondence postulates, or whether he makes it a little bit longer by prefixing some 20, let's say, existential quantifiers and replacing some constants by variables in it. But if we now think of those sentences which are much more frequent, when you read in the paper the temperature yesterday in Santa Barbara was so many degrees, and then a prognosis for tomorrow. Tomorrow the temperature probably will be so many degrees. How would we express that in LO prime? We have no word, no symbol there for temperature. Temperature in the old language was perhaps small t sub 8, let's say, just the eighth theoretical term. That has disappeared now. We are in LO prime in the language. But there we have a variable, u sub 8, which takes its place. But in order to use it and say u sub 8 for such and such geographical coordinates and such a time point is 100 degrees, so we have to write all the n, let's say 20 existential quantifiers, all the postulates, theoretical postulates, all the correspondent postulates, and then in the same operand, which is the common operand for the 20 existential quantifiers, and u sub 8 for such and such coordinates is 100 degrees. Because if you merely were to write u sub 8 of such coordinates as such and such, that would not even be a sentence, because there's a free variable in it. It wouldn't mean anything. And it would not help to just add the one quantifier, because that doesn't tell you that it is temperature. Temperature, its essential characteristics come from its combination, which are expressed, combination and connections with other theoretical terms are expressed in the C postulates, and the combination and connections with the observation terms are expressed in the C postulates. So you must give them in order to give the full sentence. Now that is, of course, rather cumbersome, and we would like very much to get rid of the T terms and still have simple sentences for those simple sentences which the physicist uses every day. Can we do that? Well, we could do it if we found a way of giving explicit definitions for all the theoretical terms in the observation language. And this is the question which I want to raise now. Is that possible? Now, I thought very briefly about that question years ago, and I just dismissed it from my mind because it seems so obvious that it is impossible. Everybody knows that the theoretical terms are introduced by postulates just because we cannot give explicit definitions of them on the basis of the observational terms alone, even if we add this strong logic. At least that seemed to be the way, and therefore I didn't think any more about it, although if we could do it, of course, that would be a great advantage. Now, it is possible. I found that only a few weeks ago, and I hope I haven't made a mistake. I have not discussed it yet with friends, except for telling David Kaplan about it, but only briefly. So I will present it here, and if somebody shows that I'm mistaken, I'm very glad before I take all the trouble of writing it in a paper, or the trouble for my wife of transcribing all that is now here on the page. So, in the hope that there may be something in it, I will now present the way of doing this by explicit definitions, which is really so surprising that I still can hardly believe it. Before I do it, I introduce a simplifying notation in the old language for the TC. I write small t for the n tuple of the t terms, the ordered n tuple t1 and so on to tn. I write small o for the m tuple of the o terms, om down to om. And so I write then, for instance, a sub t in the form of first the Ramsey and has then the simple form, there is a u such that tc uo, and a sub t, my old a postulate in the theoretical language, has the form if there is a u such that tc uo, then tc to, which roughly means this. Let's make it clear to ourselves what really in effect is said by this A postulate in the form 2. It says, if there is at least a theoretical entity U, at least one theoretical entity U, if it exists at all, such that it has the relation Tc to O. Of course, you remember U is really now an abbreviation for all the theoretical terms, so it means if these 20 entities exist which have such and such relations among themselves and such other relations to the observational entities, then let the terms T1, T2, and so on down to Tn be understood in such a way that this n tuple is one of those which are in that non-empty class. If the class of those n tuples is not empty, then let T be one of them. This is the meaning of A sub T. We'll come back to that in a moment because this is essential for finding this indeed suggested to me, this intuitive meaning of AT suggested to me the way in which to give explicit definition. Now, in order to give these explicit definitions, I make use of a logical constant that has been introduced by Hilbert, and extensive use of it has been made in the work by Hilbert and Bernays, Die Grundlagen der Mathematik. This discussed in great detail at the beginning of the second volume of it. It is the so-called epsilon operator, as Hilbert calls it. He writes an expression of it with epsilon subscript x followed by a sentential formula containing x as a free variable, let's say fx. Epsilon x fx, roughly speaking, means this. It stands if fx is not empty, if there's something that is f, the class f is not empty, then epsilon x fx stands for any element of that class. It is not specified which one. You see, this is useful in mathematics because, according to mathematical reasoning, we often do the following. Perhaps we have no example of an instance for a certain class or certain property of natural numbers or property of real numbers, but we have proved that that class is not empty by showing that if we assumed it were empty, that would lead to a contradiction or in some other way. And then we say, or even if we have instances, but we do not bother to specify which one we mean, then we say, let A be any one element of that class, meaning by that I will now go on under the assumption that A is an element of the class F, and I will not presuppose anything else about A. So all I will presuppose about A is that it is an element of the class, and then I go on and draw my conclusions from it. And indeed, this epsilon operator has been found extremely useful, especially in mathematical considerations. And Hilbert and Bernays give a detailed discussion of its value and its use and the make use of it, and then later also of its eliminability in order to show that it is not essential to have it. It is introduced for convenience, but we can dismiss it and then prove still the same theorems for another mathematical system which does not contain it. If we use this symbol, then we don't need the quantifiers, the ordinary quantifiers, existential and universal, as primitive. First, you see there Hilbert's axiom, which he gives, which says if y is an f, in other words, if we know at all that there is something which is f, then epsilon x f y is an f. So what I said is the intuitive meaning of the epsilon expression is expressed by this axiom. That's the only axiom for the epsilon operator. Now he defines explicitly the existential quantifier. You see the formula and the universal quantifier. And therefore, and then on the basis of his one axiom, he can show all the theorems of first order logic for the quantifiers. So it is actually a very elegant and effective basis of it. It is also very strong, and that may give rise to some doubts about the legitimacy of its use. I will come to that later. So now I will characterize the form which I call form 3, which of the system which contains A sub O and P in the old form, but replaces AT by AT prime, and AT prime consists just of explicit definitions, first of small t, then of t sub 1, and so on. The explicit definition of t is very simple. I call it AT0, and it is the following. T equals epsilon u Tc uO. In other words, T is the epsilon object of Tc. The epsilon operator was sometimes called also by Hilbert a selection operator because it selects an arbitrary element of the class. And now you see, when you look at this definition was suggested to me by the meaning of the AT, which I said before, which told us that if there is anything at all that stands to O in the relation Tc, then T should have this relation. Therefore I said, then T is just the selection object, that is the object which we can name by the epsilon operator applied to Tc. And so it suggested this theorem. Of course, it suggested, only didn't prove that the theorem comes to the intended result, but that can easily be shown. I will not go into details, but merely mention what can be shown on spaces. First, having the T, then we can easily define any Ti where I runs from 1 to n as m sub I of T, where m sub I is a functor, meaning the ith member in the n tuple T, which can very simply be expressed by the customary iota operator and existential quantifiers, which I will not show here. I will rather show the following. Let's start with H2, which is the Hilbert's definition of the existential quantifiers. It is written anew there. From that, we see that on the right-hand side, the epsilon expression, epsilon u Tc uO, occurs, which is just the definiance in the definition which I just proposed. So according to that definition, we can now replace it by small t. If we do so, we have there an biconditional, and if we change that to a simple conditional, we have, if there is a u Tc uO, then Tc to, which is our old postulate At in the form 2. So you see that here, from our new postulate A sub t prime, which contains this n plus 1 explicit definitions, we can logically derive the old A sub t. And we know already that from P and A sub t, we can derive Tc. Therefore, from the new A sub t prime, together with P, which we remain unchanged, we can derive Tc. That is, if we keep the whole language, then in form 3, we can derive Tc from this system here. So this system really fulfills everything that we have. It is logically equivalent to the old theory, not only O equivalent, but as this form was, but logically equivalent to the whole theory. So it fulfills its purpose, it seems to me, and still we are in the observation language. And there is only the one question left. You might say, what I said does not quite fit to each other. First, I said there is only an incomplete interpretation for the theoretical terms. Nobody can specify them, can specify their interpretation by merely referring to the observational terms. And then later you will say, you claim to give explicit definitions of them. No, obviously that is incompatible. If we have no complete interpretation, then we have no possibility of an explicit interpretation. Well, you are right, or you would be right, if we were allowed only the observational terms and customary logical constants. But the Hilbert epsilon operator belongs to a small class, there are a few other examples, of logical constants of a very peculiar kind. I will call them indeterminate. They are so that their meaning is not completely specified. Namely, in the sense, if you write down the epsilon operator, epsilon n, let n be a variable for natural numbers, n equal 1 or n equal 2 or n equal 3. Then this total epsilon expression is an element of the class consisting of the elements 1, 2, or 3. So what we know is that, let's abbreviate it by A, that either A is 1, or A is 2, or A is 3. But if I write A is 1, or it is not the case that A identical 1, there is no way of finding out the truth of this. Not because of lack of factual knowledge, it is not a factual sense, there are only logical constants in it. Not because of lack of logical information in the sense of that I do not see quickly enough the logical consequences. Its meaning, the meaning of A, has, by the epsilon operator, has been specified only up to a certain point. It is not any of those numbers which are outside of the class consisting of 1, 2, 3. More is not said. Just that is said and not more. So we cannot determine whether it is one or whether it is not one. Now, you see, this indeterminacy is just the one which we need for the theoretical concepts if we use this this explicit definition which I used in my definition of T, because of small t, I defined T as that selection object which has the relation Tc to O. That meaning, not that is really not right. Any one, if there are such objects, then any one of them is may be taken as denoted by this epsilon expression. And this is exactly what we want to say by the meaning postulate. So this definition says gives just so much specification as we can give, and not more. We do not want to give more, because the meaning should be left unspecified in some respect, because otherwise the physicist could not, as he wants to, add tomorrow more and more postulates and even more and more correspondence postulates, thereby make the meaning of the same terms more specific than they are today. So it seems to me that the epsilon operator is just exactly the tailor-made tool that we needed in order to give an explicit definition that, in spite of being explicit, does not determine the meaning completely, but just to that extent that is needed. So that will conclude my talk. If there are any questions, then. I realize it's really already lunchtime, but if a few of you are hardy souls and can...
I want only to request that all the questions be kept brief, because we are under severe time constraints. Kind of leave yourself for reference there.
Yes, please. Any questions? Or I cannot, my eyes are closed. Oh, please.
Going back to the part of your program to distinguish between synthetic and analytic, would you then say that the synthetic sentences in the theoretical language are those which are P-true and not A-true? Because
yes.
those that are A-true are
No, oh yes, if we mean analytically, yes, that's right. No, they need not be P-true and not A-true. I think we should also call as synthetic such a sentence as the temperature now is so and so much, which is not P-true because it does not follow from the laws alone, but is factual.
Any sentence that satisfies your definition of A-true also satisfies your definition of P-true.
Yes, but there are sentences which are not... what was...
Yeah, my original question was the synthetic ones are those which are P-true but not A-true.
No, synthetic sentences may also be false. So synthetic means the same as...
Synthetic truths, I'm sorry.
Synthetic truths is...
true but not A-true.
Yes. No. Synthetic true are true but not A-true. And synthetic means A indeterminate.
In passing to the Ramsey sentence and all these various alternative forms of physical theories, you require a higher order logic, don't you?
Yes.
Because you need variables referring to the theoretical predicate set.
Yes. And real numbers, functions of real numbers, all we have in theoretical physics.
Now, some people might regard this as perhaps less satisfactory than the original form of the theory. This means some people might prefer to have a first-order language, but with theoretical constants whose meaning they couldn't exactly specify, rather than these variables of higher order. Let me mention, however, that it is possible to eliminate theoretical constants by remaining always within a first-order language.
Oh, of course, I did not say they must be of higher order. They are of higher order only if you take a type system and restrict the first order, let's say, to natural numbers or something, or another sort to observable object. I said before that this higher order may be a type hierarchy, so a type logic, or maybe a set-theoretic logic.
I see, but in case of set theory, you need some special assumptions on the theory. In particular, David and I were thinking of this. I think you need to require that you can prove in the original theory that there are at least as many objects as there are theoretical constants.
Oh, you need a lot of assumptions, of course. I mean, you want to have all the natural numbers and the real numbers and function of real numbers and so on in the ordinary sense. In addition to what we presuppose in the observation language, namely observable objects.
Your approach always presupposes that the theory is such that you can prove that there are an innumerable number of individuals. You would always either put that into the logic of the theoretical language or add it as a theoretical postulate of some sort.
Even in the logic of LO prime,
yes.
I would have, of course, I would have the whole arithmetic of natural numbers, whole theory of real numbers, and so on. Oh yes, now I come back to what I said in my comment on David Kaplan's paper. You see, from this point of view here, we do no longer make a distinction between significant and non-significant. For instance, if you take Ramsey's form, there are no theoretical terms. Even if you take the ordinary form, then if you take theoretical terms and introduce them by the explicit definitions which I gave, you do not want to say that any term introduced by an explicit definition is non-significant if the terms occurring in the definitions are all significant. So I think on the basis of these considerations, it seems plausible to give up the attempt of making a distinction between significant and non-significant within this language. Of course, a term that does not belong to this language at all, and where, let's say, the absolute, as used by the metaphysician, I do not know in what logical type he has it, but if he says, it is one natural number, only he cannot yet specify whether it is greater than 7 or not, then I would say yes, then it is at least meaningful, but not yet completely specified. Now, but we can make a distinction between redundant axioms and others, because if we split up any theory which we have in such parts that the whole is, the content of the whole is not changed by leaving out the second part, then we call that a redundant part. Now it turns out that in the example which David Kaplan gave there, the axiom in the first language, the axiom n equals n is redundant, and in the second part, this and the definitional formulas are redundant. And if we say that any terms of the language we call redundant, if they occur only in redundant postulates, then in the first language, m and n would be regarded as redundant. As he said, it seems plausible to reject them. But in his second language, m and n and his 4 defined terms would all be redundant. So they are not regarded as non-significant, but they are regarded as redundant, which does not necessarily mean that they are useless. In that case, we might regard them as useless, but there are many terms which are redundant and not useless. For instance, in the third form, all the theoretical terms are redundant because they are introduced by theoretical definitions. only here they are not redundant in the same sense because they are not specified. So we might say that here we could make a distinction between those which are introduced by explicit definitions on the basis of determinate terms alone and those which use indeterminate terms like the Hilbert epsilon operator. I have not yet thought through whether such a distinction might perhaps be useful.
It is the invariable experience of anyone who talks with Professor Carnap and listens to him, however briefly, he's insensibly led to view the truths of species genitatis. But my host had assured me that local 274 peculiar language movement works in very temporal perspective, so it was with deep regret that I'm afraid